Okay, thank you all very much for coming here today. Just first of all, a little bit about myself and why I'm here. So I am Craig Box, that's my Twitter handle. I'd love to hear from you all. I work on the Google Cloud Platform, which is Google's project to externalize the infrastructure we have and make it available so that everyone can run their business on the same infrastructure that we do. I'm based in London. I've come here this morning, just literally running on the train, so I'm sorry that I hadn't announced that I was here. But I'm originally from New Zealand, and so there's a picture of me outside my house in New Zealand. So in this audience especially, but to everyone, I think it's neither unpopular nor untrue to say that open has won. And you say, we've gone from a world where we see open source as a cancer. In under 10 years, we now see this chart was published a few days ago. And actually, if you combine the Google and the Angular organizations, you'll see that they would be number one on that chart, but for some reason they didn't do that. And this isn't just altruism, obviously. This is good business, because money is now made in hosting. So Joel Spolsky, who used to work at Microsoft, he's always said that you commoditize your complements, economic terms. And Microsoft are becoming a services business. And software is the complement to hosting. So the more software that they or other people give away, then the more hosting services that they or other people can sell. So let's turn the clock back a little bit and see how we got here. So we're going to consider an average startup from 20 years ago. Here's one. It's called Google. I hope they do well. In the middle there, you'll see what Google looked like before it was incorporated as a company. So in the early days, once it was incorporated, we moved to slightly better hardware, but we didn't even have the money to pay for things like cases. So we'd just build computers on corkboards and put them in the rack. In that situation, there's no way that you can afford to pay for proprietary software and still be able to bootstrap your company. So this startup has two simple things that it wants to do. It wants to download everything on the internet, and then it wants to analyze it over and over again. That shouldn't be too hard in 1998, should it? Well, they were based around Stanford, so they could have called up Sun and said, we'd like the biggest computer that you have. We want a computer big enough to put the internet on. Well, the internet wasn't that big these days, but it still wouldn't have been possible. If you remember the Alta Vista search engine, that was actually a demo to sell DEC's computers. That was what they used as the demo. And DEC don't make computers anymore, but Yahoo's still in business. So think about that in terms of the relationship between software and hardware. Another way to look at it through the pop culture lens of 2002, the internet was still pretty big even back then. So we took ideas from all over the academic community to come up with a method for doing parallel processing across all of these cheap computers. We called it MapReduce. And Google came from the background of computer science, so we published an academic paper that suggests this is the method that we've come up with to be able to parallelize and build a distributed system to index the internet. And then in order to store it, we also needed a file system. So we came up with the Google file system and again published a paper on that. What happened was somebody took those papers and said, that's fantastic, I'd like one of those. And then they built their own implementation, and they made that available open source. And that was Doug Cutting, who was working at Yahoo at the time. And we ended up with a divergence. So we have an internal system at Google that's written in C++, and it's very, very fast. And then the rest of the industry, well, they get the Java implementation of it. So what are you going to do? And we'll come back to that story a little bit later. Now, Google very quickly became famous for its 10 blue links that load very, very quickly. What we had to do is we had to serve that index very, very quickly, but in the meantime, we needed to build it. We needed to constantly be going and downloading and processing that. And what we did was we had two separate pools of machines. We wanted to be able to serve very quickly, so we'd have a serving pool, but then overnight, when people aren't searching for anything, those machines are sitting around and they're not doing anything. But the good news is that if someone wants to run a MapReduce and some intern, for example, they can't use up all of the servers that are hosting Google.com by mistake, because everyone gets a lot of autonomy inside. They could quite easily use up all the CPU quota. There's the second task there. We had two different systems to manage those two different things you could do. For the real-time work, we basically just wanted to say, serve and then if the serving process goes down, start it back up again. That's all it should be doing, and that was called babysitter. And in order to run all the MapReduce tasks and all the batch work, we came up with a system called the global work queue, which is to allocate work out to machines, ask it to happen, and then bring it back in again at the end. And ultimately, we wanted to be able to say, well, we want to run all of our machines as one big pool and then allocate work to them as and when it makes sense. But we've got the use case where the intern says, I want all the CPU resources and runs away with it, and then you can't do your serving. So we needed a way to guarantee that the more important tasks, which of course are the ones that make money, are the ones that would get the resources. So our engineers came up with a feature which was developed in the upstream Linux kernel, was originally called process containers, but then became known as control groups or C groups. This was released in 2006. And it's a facility to basically take a process and say, this is a guaranteed priority. It's going to get up to this limit, but no more. And that lets us start packing these things together. It lets us say, we can give guaranteed priority to the serving tasks, and anything that's left over we can give to batch. The system we came up with is what we still use today. It's internally known as Borg, we'll put that in quotes, as for a long time it was very top secret. It was the efficiency, it was the secret sauce that made the company more efficient than competitors. And there's no way that we'd ever open source this. That's the thing that's very special. For example, we've estimated over time that the system of packing batch and serving workloads on the same machines, if you wanted to separate them out today into different clusters, you'd need 25% more machines. Or another way of looking at it, it saved us the cost of building an entire data center, which costs multiple billions of dollars over the course of a lifetime. So we didn't want to let other people have that same advantage who are running similar kind of companies, but we still wanted to contribute in the academic space. So the first thing we did was we wrote a book. We wrote a book on warehouse scale machines. And if you asked me to summarize this book in one sentence, it would be this. A data center isn't a collection of computers, or it can't be thought of as a collection of computers. You need to address it as a single computer. And again, if you think back 20 years ago, perhaps a system administrator could look after 100 computers, perhaps. And if you wanted to scale to however many there might be in that picture, you're going to need to hire a lot of very expensive humans. So on the warehouse scale, we've created this big distributed system. We want to manage it with as few people as possible. And then we think, well, what kind of applications will we run on this? And then we get to what we start thinking of now as the application container. For anyone who's not familiar, it's a very similar concept to apps on a modern phone. So apps are self-contained, they come as a bundle that you install together, they start up very quickly. If they crash, they don't take out everything else on the system because they're sandboxed. That's sort of roughly what an application container is. It's a way of raising the abstraction level so that instead of getting an idealized piece of hardware, which is a virtual machine, you get an idealized operating system, and you can take your code and run it on that. In effect, they're a lightweight Linux environment. There are containers available for other operating systems, but generally we're talking about Linux. We say that they're hermetically sealed and deployable. So you copy the file on, it either worked or it didn't, and then you can run that very easily, copying a file, validating it, and then if it doesn't work, you roll back. You just run the original file that you had there because everything's packed in together. And very importantly also, it's introspectable, and the artifact itself is runnable. If you think of a virtual machine environment, you can't ask the hypervisor, what's my machine doing, and then make decisions based on that, because as far as it knows, well, it's just executing instructions. In this case, you can ask the kernel that's running these processes information about what's running, and then that gets you the opportunity to make decisions about, well, where do things run? Do we want to move them around inside a cluster of machines, and so on. And it really raises that level of abstraction. And what containers allowed us to do, a number of things. We talked about the batch versus interactive case, but we can start doing things like overcommitting. We can pack more work onto a machine than it can do, knowing that people are going to try and they're going to say, I need this much resource, but they're only going to use this much, for example. We get predictability. We know that if we run a certain number of processes on a machine, that we're going to get the same performance out of that as if we run the same on a different machine. Quality of service as well, like a lot of, when people started using other cloud providers, there was what they called the noisy neighbor problem, where if you had someone else who was running on your machine who was doing intense use of the CPU, you wouldn't get as much as you perhaps wanted. So containers are a way of being able to prevent that. So we went from this world where we had server administration in the physical and virtual machine world was very much about administrating each machine individually. We talk about the metaphor of flying the plane, versus moving from that imperative model to declarative, where we say, well, we declare the state that we want. We program the autopilot. We say we want there to be enough processes running so we can serve search or we can serve Gmail or whatever your application may be. And then we let the system reconcile that. We don't have to worry about, well, if individual machines fail for so on, we don't have to go and re-rack them at the time. It's very much about the system, the controllers sorting this out in what we call a reconciliation loop. So that gives us a few great advantages. We get the efficiency. We can pack more things onto a smaller number of machines, and we can cut those costs. We have better performance because we can actively tune the environment. We can look at, say, things, well, if it turns out that because of the way they use the cache on the CPU, for example, certain things don't run well together on the same machines, they can be picked up and moved elsewhere. It lets you tie into, now this is API driven, you can tie into things like continuous integration. You can make sure that once you've done builds that they are deployed very quickly, or you can use anytime you want to push code, very quickly build that and deploy inside your cluster with that fast rollback as we talked about if it doesn't work. And as part of we talked about efficiency, we now can say, all right, well, if it turns out that it's not delivering what we want, if something crashes, if an application crashes, or if a machine running an application, we get that robustness because the system knows you've said what I want as an end state, and it knows it can get to that point. So here's a statistic that we always put up in slides. It's mostly meaningless, but it just gives you an idea that this is something that we've been doing at scale for a long time. But again, it was very secret source, and so much so that it took until we actually built a second system internally before we started talking about the fact we were doing anything about this at all. A few years ago, we published a paper on the system we called Omega, which was a better scheduling system for container work. But even at that time, we didn't even use the B word in public. It was very, very secret and internal. We definitely didn't publish an implementation. What I will do, though, is show you, here's a picture roughly of what it looked like internally. So here's a small architecture diagram. It's high level. Basically, a Google developer will configure, they'll build a binary, and they'll say, here's the configuration I want of how many of these run, and so on. And then they send that to a master, which maintains that state, provides nice management, measurement, monitoring UIs, and so on. And then a scheduler will continually go and look and say, well, I've been asked to have 1,000 copies of this. Are all my machines running? Do I have 1,000 copies? And then it will instruct an agent that runs on each of the machines in the cluster to go and run that. And again, we'll come back to this later. Now, there were people who worked at Google who went and worked at other companies. There were people who interned at Google. And a lot of people would say, for example, I really miss what I had running on Borg. I want to run this somewhere else. And there was a few people in particular who were working at Twitter. They said the same kind of thing. They said, I really miss this. And there was a talk from a guy who was working on a team at UC Berkeley who'd built a very similar system. And they thought, all right, well, we can see a way that we can turn what you've built in this academic sense into something that's a bit like Borg. And that was effectively what Apache Mesos is. It's an ideas implementation built on clustering technology from a few years ago, bringing it back into the space where you can run various, especially more data workloads onto it. Now, around about the same time, we launched our hosted VM product, Google Compute Engine. This was in 2012. It's VMs, and they run inside containers on top of our Borg platform. People started using it, and it's fantastic. And say, we're selling lots of these things. So we'd go to our capacity team inside and say, we need more capacity for the Compute Engine product because people are buying all these CPUs. And then they'd come back and look at us and say, well, hang on, you said you've sold all these CPUs, but they're only really low utilization, 5, 10, 20% or something. And say, well, why is that? Well, the Google workloads design so that you ask for exactly what you want and you pack it in. But when you sell a VM to someone, you just give them the CPU and then they only pack a small amount of work onto it. So we now have the same problem in the customer space. We have the advantages of all of this scheduling and packing work, but our customers weren't taking advantage of it. Something else that happened again around the same time was that someone had developed a pretty face that sort of sat on top of the container technology, which was still in the kernel as LXC, for example, C groups, and put real nice face on this kind of stuff. And this is, of course, Docker, which actually started a French company called .cloud. Which brings us back to Hadoop from before. We'd built this wonderful system internally, but what the community was using was the open source clone or copy that was built somewhere else. And now we're starting as a company to sell services to people and sell cloud things. We don't really want to make the same mistake again. After we'd published the MapReduce paper, we also published a paper on a thing called Bigtable, which is our internal NoSQL database store. And again, people in the Hadoop community built an implementation of that, and that's called Apache HBase. And what we want to do now is a couple of years back, is say we want to sell Bigtable as a service. We're going to make this a cloud service that people can buy. But because this is a proprietary thing that only Google run, we don't want people to feel locked into it. And we came up with an interesting solution. So what we do is we expose the original internal Bigtable service using the HBase API. So you can use it on our cloud, and if you want to move somewhere else, you can run the other implementation of it. And it's an interesting lesson there because you can differentiate on an implementation of something as long as the interface that you use is open. But given that, we actually wanted to go a step further this time, and that's where we got to Kubernetes. So we released Kubernetes as an open source project in public on June 2014. Why did we do this? Well, distributed systems are still very hard. If you've ever tried to work with them, you know you start dealing with non-atomic transactions, partial availability and things. There's a whole lot of things you have to worry about in your application without re-implementing service discovery and sort of re-implementing the wheel. So Kubernetes is a toolkit which abstracts all of this away for you. It builds on the patterns of Borg and Omega, and it has a lot of the same engineers who built those two systems working on it, but it doesn't make all the same mistakes. It's written in a modern language, so it's much easier to hack on. And ultimately, we wanted to make it as easy to build a distributed system, something that can run in a cloud provider that has these potential failures, as it is to write Hello World in your introductory computer science class. Here's a little bit about Kubernetes. It's a Greek word. It means helmsman, so you think of the pilot of a container ship, which is a good metaphor. Very early on, we talked about, well, what are we going to run inside this? And Docker containers had the open mind share. People were out there using this technology and starting to build on it. And we actually open sourced our own internal container driver, but then we saw, well, Docker's taking off, and we rolled the interesting things from that into their libcontainer project. Because you need to be where people are. You need to be, to win their business, you need to adopt the things that they're using and then help guide them in a direction which is an advantage. We also now support other container technologies. So the company CoreOS have built an engine called Rocket, and they've built an open specification called AppC, uses that. And we're starting to see other implementations as well. From the beginning, we wanted this to be something that supported multiple cloud and bare metal environments. We want it to be as an API that you use on whatever environment you run. And again, it gives you that portability to run a workload wherever you choose. And alongside that, we know that not everyone's going to build a cloud or a container application on day one. You need to be able to connect out to your other existing services, other things cloud providers run. It's informed by our internal experiences, but open sourcing Borg wouldn't have done anybody any favors. It's a 10-year-old piece of spaghetti that's designed exactly to fit our needs. We wanted to build something that was written in Go, for example, because it's the language that people working on things like Docker and Console and various other projects are using. And we ultimately boiled down to we want to let the users manage applications rather than machines. This is a high-level architecture diagram for Kubernetes. Is it familiar at all? These are all the things that you don't have to worry about if you're using cluster management. So worrying about where containers should run, whether they're running despite failures, taking a service that runs with a set of containers, making it bigger or smaller automatically if you want, figuring out where containers are. So one of the bigger lessons from the move from Borg to Kubernetes was that we would just allocate a port on the host machine in Borg. So if you were a web service and you landed on a machine that had someone else running a web service, you might not get port 80 because that wasn't available to you. So by giving each Kubernetes pod, group of containers, its own IP address, you can guarantee that you're getting the port that you want. And that, for example, lets you do quality of service inside your network because you control that space. Can distribute traffic, run a load balancer across sets of containers and tie into external load balancers. You need to be able to provide external storage outside of your cluster and connect that in. Track what's happening to your containers and services. And then to enter and attach for introspection. Finally, control who can do things. These are all services that sort of come in the box and provide integration with other things you would otherwise have to build yourself. Alongside Kubernetes, we came up with this concept we call cloud native. And cloud native means dynamically scheduled applications, container packaged, microservices oriented. And so Kubernetes is really one leg of that stool in order to be able to run these things that will work well on cloud environments, either public or private. It's been GA since 2015, and we're about a week away from the next major release. Interestingly, under half of the code in the project is now written by Google. We've seen a lot of collaboration from other commercial open source vendors like Red Hat. We've seen a lot of collaboration from community groups, from colleges, people doing hacking on it internally. But it is really a good example of something where we're still actively involved and contributing to it, but we've actually built a big open source ecosystem around the project. And in order to make people understand that it's not just a Google thing, this is something we really want everybody to run and benefit, we set up a foundation working with the Linux Foundation for cloud native computing. And then we gave the copyrights and the trademarks and all of the code to that foundation. So it exists as a community thing outside of Google. It takes a lot of these lessons from people who are battle hardened at running production systems. It moves at the right pace. And there's some very important things here is that we really wanted to say, here's the API that we trust and we're going to support, and we're going to make changes in the new version, and we'll have alpha and beta tracks and things. But a lot of products in this space are very much still sort of pre 1.0 quality, even though they've got a 1.0 label on them. This is something that we wanted to say, we've had the production experience, we want to make sure we don't make these mistakes again. We've got the core very sensible, and we're seeing development both in terms of development on the project and extensions. They're now sort of happening outside the core. So we're seeing people who are now moving on from what can I run on my cluster to how can I make the cluster support the kind of workloads I want to do? How can I build custom schedulers that are aware of the kind of things I might want to run? So we're not going to go too deep into the technical details here, but the core primitives say you run, effectively you just describe the work you want to run in the containers that have your programs in them. And then you deploy them by way of pods, and services are abstractions that let you address a group of pods and handle that load balancing. Again, another thing that we picked up that was something we wished we'd done in Borg is it's all label addressed, so key value pairs on things, and then you just say, I want to address the things which have this label, and then you're able to sort of do a selector across your running work to say, for example, this load balancer targets things that are a type front end in version 2. In the Borg world, you only had one ID, so you have people have a job called Gmail-v2-2014-server name or so on, and a lot of these things are very hard-fought lessons. So on top of those basic concepts, we're starting to say, all right, well, how can we extend things? So we have the ability to run work and replicas of things, and then we say we want to run the batch work. So we want to say run something not forever, but run it until it completes. That's a job. And then the 1.4 release, we're seeing scheduled jobs, which is basically a cron service. We say do that, but do it at a certain time. So it's continual iteration over the set of things that we're built on. We've seen an absolute great uptake from the community, both in terms of more commercial vendors from the past and a lot of people doing commercial open source, as well as a lot of other open source projects. So we're working with a number of cloud providers. We ultimately want to see everyone with a hosted Kubernetes offering. Companies like Red Hat and CoreOS doing distributions of Kubernetes to run behind the firewall. A lot of people are working on platform as a service offerings. So Deis is a good example there. It deploys just as something that runs inside your cluster, and then it gives you a Heroku-like environment where you just push code and then it does all the building and deploying to that same cluster. They were, along with OpenShift, they were sort of running in a different platform in the past and said, well, hang on, if we re-platform on Kubernetes, then they give us all of the things you saw on the previous slides for free, and we can focus just on adding value at the part of the stack, which makes sense for us. Have a number of tools around networking. So the way our networking model works, it takes a bit more to set up because you need to have a flat network between all of the machines. And again, that's something we make it takes a little bit more work at the beginning, but that makes deploying applications easier throughout. And that's a model now we've seen picked up by other people working in this space as well. These are numbers from a couple of weeks ago, but they're still about right. We've had, say, now over 35,000 individual commits for almost 1,000 people. And we're seeing it picked up by a lot of companies for their internal production workloads as well as web-facing stuff as well. Google run a managed service that let you run just by clicking a button and getting a cluster. There's a nice free trial if you're interested in getting started. It's also very easy to run. We have a new tool called Minikube, which lets you run just on your laptop and deploy a cluster there to do your testing. And an area that we're seeing a lot of active work at the moment is in that cluster turnup, because there are a lot of moving parts in getting this working. So for anyone who's interested, there's an alpha now and it's coming out with 1.4 of a new tool which makes it easy to, basically one command to set up a Kubernetes master, then generates tokens which you then give to the same command that you run on the nodes, and that will connect up. It'll do all the TLS negotiations, certificate swapping and things, so you end up with a secure cluster, and it's a lot less ball of scripts to set up. So there was an interesting article that was published about a week ago in InfoWorld by open source commentator Matt Assay. And his theory is that why Kubernetes is doing so well at the moment is really about the open source community that's been built around it. And there is obviously the pedigree of the background that we have in this, but his point was to say that it's about building an open source community. And in his article, he sort of suggested it was you build something and let it go and then just sort of hope that it works. Whereas one of the things we think about this is it's not as much as that, but it's the maintaining involvement from our engineering team. So we are still working. We are working with product people from the community. It's now sort of feature development is done in the open as well. But the choices that are being made and the engineering contributions still being brought in by Google is sort of helping drive the project. And I think I want to emphasize that if you are a commercial company looking to build something in open source, you can't just put it out there and say, right, it's yours to maintain now. It is still needs that drive. And the quicker you can build your community of contributors to include people from outside your company, the better. But you still need to, as if you're in this kind of environment, provide a steady hand in cases it needs it. So just to end up here are a few things we think Kubernetes sort of engages and lets people do. So you have operations teams are happier because it's very easy for them to operate this kind of environment. Application developers are happier because they have a nice interface where they sort of hand things off. It enables sort of reliability of infrastructure automation. More efficient use of resources is a way of saying lower cost. And lower risk as well. These things enabled by the container and cluster deployment pattern. If you have developers who are so scared of their legacy code base that they don't ever bother going and changing things, then again, that's a problem that people have. So the concept of microservices is a way of breaking that apart and saying, all right, well, let's make everything so simple that everyone can understand it and then build the boundaries between them, well-documented APIs. So thank you very much. I think I have some time here for questions. But otherwise, do feel free to tweet at me afterwards. So thank you.